Good morning, ladies and gentlemen. I'm Hayder Al-Jelawy, a PhD researcher at the University of Northampton, as Rory said. My supervisors and the co-authors of this paper are Professor Stefan Kaczmarczyk and Dr. Saeed Mirhadizadeh, also Dr. Durgham Al-Khafaji. I'm happy to be here today, and thank you for the opportunity to present my paper entitled A Study into the Influence of the Car Geometry on the Aerodynamic Transient Effects Arising in a High-Rise Lift Installation, which forms part of my PhD research. In this presentation, I'm going to cover these 6 main areas. Firstly, I will give an introduction and the aim of the paper, and then I will introduce the governing equations. Point number 3 will be the model designs. The computer simulation results will be point number 4. And then I will discuss my results and present the conclusion of this paper. Well, the fast development of high-speed lifts has been facing significant challenges related to the aerodynamic effects and problems such as a high air resistance to the car movement, vibration of the car, of the lift car, excessive pressure fluctuation and noise generated inside the car while it's moving along the shaft. These problems occur because of the high-speed airflow around the moving high-speed lifts, which increases around sharp edges. The ride quality is very important for the passengers' safety and comfort. Accordingly, it is essential to understand the aerodynamic forces and mitigate their effects. The aim of this paper is to investigate the impact of aerodynamic effects on different lift car geometries and to improve the ride quality and reduce the energy consumption. A 3-dimensional incompressible Newtonian fluid has been considered in order to develop a mathematical model and also to have a better understanding of the flow. The transport flow variables are governed by 2 basic physical principles, which are the conservation of mass, equation number 1, and the conservation of momentum, equation number 2. These 2 partial differential equations are called Navier-Stokes equations. The variables that I'm interested to calculate are the pressure and the air velocity. The parameters of these 2 equations are the mass density of air, body forces, and also the shear stress in the fluid. The computational fluid dynamics modeling process has been done by using different commercial platforms. It involves creating the geometry using SolidWorks software and creating the mesh domain and setting up the case using MSC Patran software. Also, MSC Dytran has been used for the simulation run in parallel. Eventually, visualizing the results by using ParaView software. This figure shows the 3 simplified CAD designs of the lift car. As you know, most of hoistway have rectangular cross-section. Therefore, this study considered a car with rectangular cross-section as well, equipped with different top and bottom aerodynamic shroud shapes, as you can see here. This study also considered two assumptions for the flow and for the structure. The flow was three-dimensional incompressible flow, as I said, and the structures are treated as rigid bodies. An explicit solver based on finite volume method is used to solve the Eulerian system of the flow equations, which forms a model to predict the dynamic behavior of the flow around the car. Also, finite element method is used for the structural parts of the problem. This figure shows the cross-sectional area of the simplified hoistway. The hoistway height is 90 meters, and the initial time at t equals 0. The two cars are actually located 12 meters apart from each other. The horizontal distance between the two cars is ½ meter. Large Reynolds number results 2.6 million. This would clearly lead to consider the flow as a turbulent flow. To clarify my scenario, this figure shows 5 different time stations for the vertical motion of lifts, and at t equals 0, we have the two cars are moving 12 meters, are moving at a constant velocity 20 meters per second, and they are located 12 meters apart from each other. The cars will be aligned side by side at t equal 0.3 seconds, and the crossing event will be finished at t equals 0.6. So this is the scenario and should be okay. Now, this figure shows the air field and its velocity profile around each car, and it shows also the pressure distribution over the car's bodies. It can be seen that the pressure value that acts on the flat lift is higher than other shapes. Also, at the crossing event, it's clear that the air pressure that acting on the triangular lift is less than the air pressure that acts on the hemicylindrical lift. I would like to say here that the pressure load fluctuation could cause noise and vibration which could transfer inside the lift cabin. This pressure would be building up and reaching its highest values at the crossing event, actually. These two graphs show the pressure fluctuation over the side walls of each lift. Graph A is for lift number 1, which is going downwards. Graph B is for lift number 2, which is going upwards. For those who sit in the back, the vertical axis is the pressure. The horizontal axis is the real time, from 0 to 0.6, which is not the simulation time. At t equals 0.3, as I said, the cars will be aligned side by side, and you would notice that the highest values of the pressure occur at this time. The blue line is represents the pressure that acts on the flat lift, which is 99.1 kilopascal, and the green line represents the pressure that acts on the hemicylindrical lift. The red line represents the pressure that acts on the triangular lift, which is the lowest value in here, which is 97.7 kilopascal. one of the main forces that act on the lift bodies is the drag force. The drag forces have been determined with a simulation test where the gravity effects removed. It's clear from the red line in here that the drag force that acts on the triangular lift is less than the drag forces that are acting on other shapes. From these two graphs, A again for lift number 1, B is for lift number 2. The resultant overall force as shown in this figure. This fluctuations shows the overall forces that are acting on the lift surfaces. Now the color coding has been changed. The red line represents the resultant force that act on the flat lift, which is the highest value, 46.8 kilonewton, and the green line represents the resultant force that act on the hemicylindrical lift, and we have the lowest value, 23 kilonewton, which acts on the triangular lift. The drag force have an effect on the flow in the wake region of each lift. In this kind of engineering problems, predicting and modeling the shear layer separation is very important because it will have an important influence on the opposite moving lift, because we have two lifts passing each other. This figure shows the airflow patterns and its velocities in the hoistway. It's clear that the turbulence behind the flat lift is much higher than the turbulence behind the other shapes. Furthermore, the flow behind the triangular lift tends to reattach at the wall side rather than to the side of the moving lift, which is lift number 2, which is going upwards. Thus, lift number 2 will experience less turbulence than other shapes. Okay, this animation shows the air velocity vectors in the hoistway, and also it shows the pressure distribution values over the cars' bodies, and you can see clearly that the pressure that acts on the triangular lift is again less than the pressure magnitude that act on the other lifts. Also, high velocity profile behind the flat lift can be observed. Okay. To conclude, the influence of different lift car geometries on the aerodynamic performance of lift has been discussed in this presentation. Also, the scenario applied involves two lifts are passing each other in the same hoistway. Flow patterns, velocity, pressure, drag forces, and resultant force have been calculated. It was revealed that the lift car geometry design plays a significant role in the aerodynamic performance of the lift. From the aerodynamic point of view, my results indicate that the triangular shape of the lift top and bottom aerodynamic shroud would be the best design in comparison with other designs. And also, I believe my results would be helpful to the designers to consider the aerodynamic effects in the design process. Thank you very much.